We now focus specifically on the resolution of a vector into orthogonal components in 2 dimensions. Our standard 2-dimensional Cartesian coordinate system looks like this, with the positive x direction pointing to the right and the positive y direction pointing up. Let's call the angle between v and the x-axis theta. In our previous section, we noted that the component magnitudes of the vectors along x and y could be easily written from trigonometry as Vx equals v cosine theta, Vy equals v sine theta. We now define a unit vector I as a pointer directed along the positive x-axis. Unit vector j is a pointer directed along the positive y-axis. These unit vectors have magnitude 1, or unity, and no physical dimensions. As mentioned briefly in the previous section, all vectors can be expressed as the product of a magnitude on a direction specified by a unit vector. This represents a kind of partitioning where the attributes of the vector are separated. The magnitude is expressed as a scalar quantity carrying the dimensions of the physical entity, and the direction is expressed as a pointer or unit vector having magnitude 1 and no dimensions. We could therefore write vector component Vx as scalar component Vx in the I direction equals v cosine theta I, and vector Vy is scalar magnitude Vy in the j direction equals v sine theta j. If we wanted to be a bit more careful, we could say that the scalars Vx and Vy represent value instead of magnitude. Magnitude is a positive quantity, and the components Vx and Vy could be negative as well as positive. In these first illustrations, we have sketched the vector in the first quadrant, where Vx and Vy are both positive, so there is no distinction between value and magnitude. Suppose, though, that the angle phi is obtuse, as sketched here. The components are still v cosine phi and v sine phi, but now Vx is negative and Vy is positive. In most instances, it is more convenient to work with acute rather than obtuse angles, and we work with smaller angles to find off axes other than the positive x-axis. If we define psi as phi minus 90 degrees, then we would say Vx equals minus v sine of psi, and Vy is equal to v cosine psi. We might also simply say the x component of v is v sine psi in the minus I direction. Recall that in the previous section I referred to the weight as having a magnitude mass times gravitational constant acting in the minus j direction. In any event, there is no reason to get too hung up on the language. Once a coordinate system is defined, we should be able to see what directions vectors are pointing and assign positive or negative values to the components based on their quadrant location. An important part of orthogonal decomposition is recognizing the independence of these mutually perpendicular directions. In our orthogonal coordinate system, vector Vy has no component in x, nor does Vx have any component in y. On the right side, we have a non-orthogonal decomposition of vector v in an a-b coordinate system with the angle between axes a and b theta less than 90 degrees. There is a component of VB in the A direction, and it's equal to VB cosine theta. This obviously goes to 0 as theta goes to 90 degrees and the system becomes orthogonal. Even though A and B are different directions, VB still has an influence on, or if you like, casts a shadow in, the direction of A. The influence of one non-orthogonal direction on another implies some dependence between them. The independence of the orthogonal component directions implies that we can examine everything that occurs in the x direction separately from everything that occurs in the y direction. This property enables us to turn a two-dimensional problem into two one-dimensional problems, one in x and one in y. In addition, this independence applies to any set of orthogonal directions, not just those associated with a Cartesian xy coordinate system. In future applications, we may use this independence in a polar system, that is an r theta system, a tangent normal system or TN system, or any other system of mutually perpendicular directions. When applied to vector addition, this independence implies that the summation in the x direction can be performed separately from summation in the y direction. Our procedure is, first, select an appropriate orthogonal coordinate system. We'll start with x and y for illustration. Second, resolve each vector into its x and y components. And then third, add all x direction components to find a resultant component in x, and then separately add all y direction components to find a resultant component in y. This slide contrasts our previous geometric approach with our current Cartesian approach. Here we begin with two vectors of known magnitude and direction, and we wish to add them together to form a resultant. In our geometric approach, we make use of the properties of triangles. The angle between V2 and V1 is 180 degrees minus the difference between theta 2 and theta 1. Knowing the magnitude of V1 and the magnitude of V2, we use the law of cosines to find the resultant magnitude r. We then use the three known magnitudes and one known angle in conjunction with the law of sines to find the remaining angles. Letting phi be the angle between V1 and r, we report the resultant as a vector having magnitude r at an angle theta 1 plus phi off the x-axis. Using a Cartesian approach, we resolve each vector into its x and y components. Then note that the x and y components of the resultant can be found from summing the x components and the y components of the individual vectors separately. The value of this approach is that it can be extended to the addition of any number of vectors without complicating the problem. We don't have to be able to see relationships between vectors as we do in the geometric approach, and we don't have to make decisions about whether to analyze triangles versus more complicated vector polygons. Once the x and y components of the resultant are determined, its magnitude and direction can be obtained from these expressions. As indicated earlier, the magnitude of a vector is a positive quantity and should be reported as positive whether one or both components is positive or negative. The orientation can be found from the arctangent, but here we have to be a little careful with the number produced from a calculator. Consider first the case where Vx is equal to Vy. This could be true with Vx and Vy of equal magnitude and both positive or both negative. In either case, the ratio is 1, and your calculator will probably tell you that the arctangent is 45 degrees. But it would be more precise to say that the arctangent is 45 plus or minus 180 degrees, with a need to select the appropriate value based on the quadrant the vector occupies. If both Vx and Vy are positive, the vector occupies the first quadrant and the appropriate value of theta is 45 degrees. If Vx and Vy are both negative, the vector occupies the third quadrant, and the appropriate value of theta is 225 degrees or minus 135 degrees. Similarly, if Vx is equal to minus Vy, the vector could be in either the second quadrant, that is with Vx negative and Vy positive, or the fourth quadrant with Vx positive and Vy negative. The ratio of velocity components is now minus 1, and your calculator will probably tell you that the arctangent is minus 45 degrees. But this should again be thought of as minus 45 plus or minus 180 degrees. If the vector is actually in the second quadrant, the angle should be 135 degrees or minus 225 degrees, and if in the fourth quadrant, it should be minus 45 degrees.